In question number 6, a gaseous mixture enclosed in a vessel consists of N1 mole of gas A with gamma is equal to 5 by 3 and 2 mole of gas B with gamma is equal to 7 by 5 at a temperature T. The gases A and B do not react with each other and are assumed to be ideal. If gamma of the gaseous mixture is 19 by 13, then the value of N1 is. So we know that CV gamma mixture is equal to R divided by 1 minus gamma mixture. So the value of gamma mixture is 19 by 3. So if I substitute the value of gamma mixture 19 by 3 here, then it comes out to be 13 R by 6. So this is the value of CV mixture. And this is equal to N1 into CV1. So the value of CV1 for the monoatomic gas, because gamma is 5 by 3, that is equal to 3R by 2 plus N2, that is 2 into CV2. Since the second gas is diatomic, so its CV is 5R by 2 divided by N1 plus 2. So if I solve this equation, the value of N1 comes out to be 1. So option 1 is the correct answer. Let's move to question number 7. In question number 7, the state of an ideal gas is changed through an isothermal process at temperature T0 as shown in the figure. The work done by the gas in going from state B to C is double the work done by gas in going from state A to B. The volume of the gas in state C is. So since the process is isothermal, so the work done in isothermal case is nRT ln V2 by V1. So I can write nRT, that is T0, ln volume of gas at state C divided by volume of gas at state B, that is equal to 2 times nR T0 ln VB by V. Or I can write from here the value of VC by VB is equal to VB upon VA whole square. Now the volume of the gas at state B is V0. So if I find out the volume of the gas at the state A, then it comes out to be V0 by 2 because the process is isothermal. So PV is equal to constant. So the ratio VB by VA comes out to be 2. So it is equal to 2 square, that is 4. So from here the value of VC comes out 4 times VB and the value of VB is V0. So it is equal to 4 V0. So option 2 is the correct answer. Let's move to question number 8. In question number 8, 1 mole of oxygen gas at 27 degrees Celsius and 1 atm pressure is enclosed in a vessel. The vessel is thermally isolated and moved with a constant speed V0. It is then suddenly stopped. The process results in a rise of temperature of gas by 4 degrees Celsius. The speed V0 is nearly. So in this case, the increase in the temperature of the gas is at the cost of kinetic energy of the vessel. So if I assume the mass of the vessel is equal to the mass of the gas, then I can write half into m into V0 square is equal to change in internal energy, that is n CV into dt. So if I substitute the data, half, so mass of oxygen gas is, that is 1 mole of gas, so it can be written as 32 into 10 raised to the power minus 3 in kilogram into V0 square is equal to number of moles is 1 into CV. Since the gas is diatomic, so it is 5 by 2 into R. So the value of R is 8.314 or 25 by 3 and change in temperature is of 4. So if I solve this equation, the value of V0 comes out to be nearly equal to 72 meter per second. So option 4 is the correct answer. Let's move to question number 9. In question number 9, in 2 experiments with continuous flow calorimeter like a geyser, to determine the specific heat capacity of a liquid, an input power of 60 watt produces a rise of 10 Kelvin in the liquid at the output end. When the input power is doubled, the same temperature rise is achieved when the rate of flow of liquid is increased to 5 times. If the power loss through the calorimeter is same in both the cases, then find this power loss. So we know that input power is given for time t, that is we can write P into T, that heat is utilized first in supplying to the liquid, that is delta Q, plus the remaining is heat loss. So if I write the equation for the first process, so that is equal to 60 into T is equal to, let the mass of the liquid which flows out from the liquid is, so M, its specificity is S, and the increase in temperature is delta T. So in this process the heat loss is let delta H. So in the second process, when the input power is doubled, so now the input heat is 120 into T for the same time interval, and the same temperature rise is achieved when the rate of the liquid is increased to 5 times. So the rate of the liquid is increased to 5 times. It means the amount of liquid flow in the same time interval is 5 times of initial amount. So that is equal to 5 into M. Specific remains same and temperature change remains same. Plus it is given in the question the heat loss is same, that is delta H. So if I multiply this equation by 5, so it comes out to be 300 T is equal to 5 ms delta T plus 5 times delta H. So if I solve this two equation by subtracting, here it comes out to be 4 delta H and here it comes out to be 180 T. So from here the value of delta H by T comes out to be 180 by 4 and it is equal to 45 watt. So this is the rate of heat loss or power loss. So option 3 is the correct answer. Let's move to question number 10. In question number 10, the temperature of water of pond is 0 degrees Celsius while that of the surrounding temperature is minus 10 degrees Celsius. If the density of ice is rho, coefficient of thermal conductivity of ice is K, and latent heat of melting of ice is L, then thickness H of the ice layer formed on the surface of water as a function of time T is. So let this is the surface of pond and here the surrounding temperature is minus 10 degree Celsius. The water of pond is at 0 degree Celsius. Let at any time T the thickness of the ice formed on the surface of water is X. Then I can write dq by dt is equal to Ka T1 minus T2 by L from the rate of heat flow from the theory of conduction. So if I write the relation L, that is the latent heat, into dm by dt, so d by dt of m. So the mass of the ice of cross section A can be written as density rho into volume, that is A into x, that is equal to thermal conductivity K into cross sectional area A into T1. So the heat is flowing from here to here, so 0 minus minus 10 divided by thickness layer is x. So from here L into rho into dx by dt is equal to 10k by x. So if I solve this, x dx comes out to be 10k by rho L into dt. So at t equal to 0, the thickness layer is 0 and at any time t, let the thickness layer is h. So if I solve this, then it comes out to be h square is equal to 20 kt by rho into L. So option 3 is the correct answer. Let's move to question number 11.